In this video, Rowan and I will talk about type II supernovae. So first, we'll talk about what a type II supernova actually is. The definition of a supernova is that it is a star that suddenly increases greatly in brightness because of a catastrophic explosion that ejects most of its mass. So before 1941, we knew that supernovae existed, but we didn't know how to differentiate the different types. But the way that we now can differentiate a type II supernova from other types of supernovae is through the hydrogen lines in its spectra. This is thanks to astronomer Rudolf Minkowski, who in 1941 he determined that hydrogen spectral lines are what let us know that a supernova is a type II supernova. So for a type II supernova to happen, we need to have a supergiant star, which means that we need it to be at least 8 times more massive than our sun. We'll talk more about it, but the mass is important for what the result of the supernova is. So in a type II supernova, the star is about to die out, so the pressure decreases in the core of the star, so that causes the core to collapse. This makes the density skyrocket in the core, and then eventually the particles, which are usually hydrogen and helium, get exploded out of the star, and a bunch of gas is expelled from the star, and this later creates this. So this is what a supernova looks like. This is after all the gas is exploded from the star, and this is what it ends up looking like. So let's talk more about the life cycle of the star. I'll reference this bottom right image. Starting at this red supergiant point, we know that the star has to be 8 times greater than the sun, and then that will allow it to later blow up into the supernova. And then if the star is really massive, then the core collapse will keep going into a black hole. And if it's less massive, the core collapse will lead to a neutron star. This usually happens after all the silicon has been burned through, so there's no more energy left in the star, and the core just becomes either a black hole or a neutron star. And most often, there is stellar recycling that goes on after. So this is why type II supernovae are often in regions of star formation, because the materials from the supernova are then recycled into new stars being formed in that region.
Now moving on to interesting physics, like Matthias was saying earlier, the whole cause of a type II supernova is that the core collapses, and then that makes the density skyrocket. And since the density is so high now in the core, the nuclear force of all the particles in the core is enough to actually repel the outer layers of the star as it keeps trying to compress to fuse more material. And it's basically just the star implodes because there is it's trying to collapse. The outer layers are trying to compress to create more fusion, to have the pressure that's required for fusion. But then it can't fuse because the core is repelling all those particles trying to fuse, and it ends up just creating a core rebound, which pushes out all the outer layers and creates a huge explosion, as illustrated pretty well in this little GIF down here. And as all the outer layers are just shot out from the star, there's so much energy, just matter, and all the material is just ejected at such a high speed that actually causes runaway nucleosynthesis, which causes a neutron-rich environment. Just has plenty of just decaying particles, or particles that are forming. Like some of the heavier ones, like calcium, titanium, chromium, iron, and nickel. All as soon as they're formed, they all decay really soon after. Another interesting part is that there, in some type 2, or before type 2 supernovas happen, they actually go beyond SI fusion, or not SI fusion, silicon fusion. Normally, most main sequence stars end there, but since some of these giant stars can undergo a type 2 supernova, they can actually compress further and fuse all the way up to nickel, which kind of includes calcium, titanium, chromium, iron. Like it fused all the way up to nickel, which is a lot more elements more than main sequence stars do. But that all that fusion, all the fusion up to nickel, all this falls under the umbrella term of SI burning, because it doesn't last too much anyways, as most of the fuel is consumed. It only lasts about a day. Now, how do we actually detect Type 2 supernovas? Well, we detect supernovas in general the same way we detect stars. We just accept that we can just look for brightness variations in the sky to indicate that a supernova happened in this portion of space, that how many billions of years ago or millions of years ago, depending on the distance. And then we align our telescopes with it, and then we gather data. Uh, so the general Type 2 supernova has a lower peak luminosity than the Type 1, as it's ejecting relatively less material out of the star, and less energy as well, as it ends up as the core ends up forming a black hole or a neutron star. Um, but like Matthias said earlier as well, the only way to differentiate between Type 1 and Type 2 is not based off luminosity, because if you have a small Type 1 supernova, it could have a less peak luminosity than a huge Type 2 supernova. So and the whole difference is through the hydrogen lines, as I said earlier. So how we find that there's hydrogen lines in a light reaching our telescopes is by doing spectroscopy, putting through a diffraction grating, and we get the data out. The data goes into these nice graphs. I have them on the next slide, but here in this graphic to the right, you're able to just to see all of like what the process is of doing spectroscopy. Like the light comes in, hits off a mirror, goes through a diffraction grating onto a camera mirror, and then to a detector. So these are the graphs compared of Type 1 supernovas to Type 2. As you can see in this Type 2 right here, there's some really strong hydrogen emission spectra right here. Same thing with here. And around this too a little bit. As you can see in Type 1, they don't really have that huge emission spectra at around 700 nanometers at all. And the whole conversion is probably just angstroms to nanometers is divided by 10 angstroms to 5 nanometers. Don't worry about that. But another way to detect is to just observe, again, with emission spectra of just like the amount of elements that are in the surrounding gas in a particular region. It doesn't actively show that a supernova happened. Well, it just shows a supernova happened time ago. It doesn't show a supernova happening relative to light traveling. Well, that's all we got for you, so thanks for watching.